So I would like to start my video by giving some theoretical background about infrared spectroscopy, which we will cover this week's lab. IR infrared spectroscopy actually involves the interaction of infrared radiation with molecules. IR region is highlighted with pink area on the electromagnetic spectrum. Remember, light is a wave of alternating electric and magnetic fields. The wavelength is the distance between two waves and is measured in centimeter. But in energy equation, if you place the wavelength, it is disproportional with the energy. If it is having higher wavelength, it will have lower energy, like in the radio waves. If it has lower wavelength, it will be having higher energy, like in gamma rays. So in order to prevent it, in IR spectroscopy, scientists use some terms. The term is 1 over lambda, the 1 over wavelength, and it will be directly proportional to the energy that way. And it is called the wave number, and its unit is centimeter to the -1. And this way it's directly proportional to energy in the IR spectroscopy. Here is a picture of an IR instrument in our labs. Your solid or liquid sample will be placed on a crystal, which is here is in the center of the sample platform. Then the IR light passes between the sample and the glass substrate and the crystal and the sample will start absorbing at specific wavelengths. So the transmitted light, the ones who are not emitted or absorbed, will reach to the detector and it will reveal how much energy absorbed at each wavelength. IR radiation causes the excitation of the vibrations of covalent bonds within that molecule. I would like to give water molecule as an example. Water molecule has two oxygen-hydrogen bonds, and they can do two types of vibrations. First one is the stretching ones, and the second one is a bending motion or vibration. So the first example is a symmetric stretching of the two bonds. They can do also anti-symmetric stretching. The bending motion can be in plane rocking or in plane scissoring motions. To make the analysis in the lab simpler, we only study stretching vibrations in the organic lab, so the bending vibrations are not included in our analysis. You can resemble bonds like springs in between two atoms, and there is a direct relationship that way between the bond strength, frequency, and energy. If you have stronger bonds, the wave frequency will be higher, and so on, the energy will be larger too. So we can give different carbon-carbon bonds as an example. The single bond, carbon-carbon, versus double bond and carbon-carbon triple bond. The single bond is weaker than the double bond. It resembles to holding a rope with two arms, and it will be stronger than holding with one arm. And triple bond is the strongest bond here, which will be higher in energy in vibrational mode. So this carbon-carbon triple bond is stronger bond and it will have higher energy. Carbon-carbon single bond, on the other hand, will be lower energy. And remember, the wave number is directly proportional with the energy. So triple bond is going to have the highest wave number. It will show absorption peak around 2200 wave number. On the other hand, carbon-carbon single bond will have low energy and low wave number, and it will show around 1000 centimeters to the -1 or wave number. Similarly, there is another factor affecting the vibrations of a bond, and that's the mass of the atoms. The lighter the atom, higher the wave frequency and larger the energy needed. Let's compare carbon bonded with different size of atoms as an example. So carbon is bonded to smallest atom, hydrogen, carbon, chlorine, bromine, and the biggest mass, iodine atoms. So because hydrogen has the smallest mass in the comparison, it has the highest energy. And the carbon iodine bond is going to have lowest energy in this comparison. So let's check their wave numbers. So carbon-hydrogen stretching is going to show up around 3,000 wave numbers because it's high energy. Carbon iodine bond, because it's big, because of its big mass, it's going to be low energy, and it will have very low, like 500 wave number absorption in the IR spectrum. So these are theoretical backgrounds. Now we can start learning the practical aspects of IR spectroscopy. Functional groups are the only useful information you can get from IR spectrum. It is important to remember when analyzing an IR spectrum, you cannot assign every single peak. You can only use it to have a general idea about functional groups in the molecule. I'd like to give some examples about IR spectrum. The most visual functional group is alcohols in IR spectrum. It shows very broad and strong peak around 3300 wave number. In this example, isopropanol shows an absorption for OH around 3350 wave number. Also, it shows carbon-hydrogen stretching around 2900, like below 3000. And it shows one more carbon-oxygen stretching around 1200s. As you see from here, I only label 3 bonds around all of these peaks. Another example is aromatic ring. In this example, I give toluene, which is a not very used solvent in organic labs. It has an aromatic ring, which consists of 6 carbon atoms and 3 double bonds, which makes it aromatic. Also, aliphatic carbon-hydrogen bond. The first thing I'm going to show you is sp2 carbon-hydrogen stretching around above 3000. And below 3000, it will give sp3 carbon-hydrogen stretching. Which one is this? Another thing is the carbon-carbon double bond around 1600 and around like 1500 from carbon-carbon double bond stretching. So all of these approximate stretching wave numbers I gave in the examples and their corresponding bond types can be found in a list, and that is posted on box folder under structure determination files. My last example about the IR will be the next one, and that consists of an ester. Esters are very unique in the IR spectrum, which has very strong carbon-oxygen double bond absorption in the middle of the spectrum. It's around 1700 wave numbers. In this example, its ethyl acetate consists of a carbon-oxygen double bond and a carbon-oxygen single bond. It also shows stretchings around 1200 and 10,050 centimeters to the minus 1. So the last list or last compound type I want to show is the carbonyl compounds. Carbon-oxygen double bond group called carbonyl, and they can be an aldehyde, ketone, ester, carboxylic acid, or an amide. They will all have absorption around 1700, but their ranges will be slightly different, so you can distinguish if it's an aldehyde or an amide. So on the right side of the slide, the IR spectrum shows maybe it's a ketone or an ester, because it has a strong carbon-oxygen double bond around 1700, and below 3000 it has CH, so it doesn't have an aromatic ring possibly. bottom one is unique because it has carbon-oxygen double bond stretching and two distinctive strong peaks around 33,000, which makes it an amide. The reason it gives two peaks here because NH bonds can do asymmetric and symmetric stretching, so it gives, instead of very broad one peak, it gave two peaks and they're strong. So the second thing we're going to learn in this lab is the mass spectrometry. When you synthesize a new compound, drug, or molecule, it is crucial to prove its molecular structure by different characterization methods. So one method is usually not enough, so we need more than one method. IR was one of the oldest and limited methods right now, so we have better techniques. Which one is, I will show right now, more useful method, mass spectrometry. Mass spectrometry gives exact molecular mass of a compound. Also, it gives molecular mass of its fragments, the pieces of a compound which can be put together like a jigsaw puzzle to kind of understand the pattern of the molecule. Fragments are ions and they are created by bombarding the molecule with electrons. It's like cutting the molecule into the small pieces. If you throw a brick to a window, it will be as small pieces, but each time you throw the brick at a new window, it will shatter differently each time. So similarly, it's going to be the same in this one. So before starting how to analyze the mass spec data, I'd like to show what's happening behind the scenes. We inject the pure sample into the instrument, like we did last week when we're using GC. Gas chromatography was actually in our lab fused with mass spectrometry, so both of them happening at the same time last week. So we inject the sample, it heated quickly around 250 Celsius degrees, so it vaporizes into the gas phase. Then the gas molecules bombarded with electrons to make them charged. And when they charge, they also start beginning fragmenting into the small pieces. Then small pieces are accelerated. So they direct it to the magnet, and then they direct it up towards the detector by the magnet. So right now, the accelerated fragments, or heavy pieces in this case, will touch to the bottom part of the detector due to the gravity, and the lightest particles will touch the different part, like upper part of the detector. The original molecule will be very less when it reaches here, so it will be less in abundant. But depending on where the particles hit, the detector gives us different types of peaks and their calibrated masses. Keep in mind, please, only the cations are formed are analyzed in mass spectrometry. So let's analyze hexane mass spectrum and its fragmentation pattern. The molecular weight can be calculated from periodic table mass values. It is expected to find a molecular ion peak at 86 gram per mole. Molecular ion is the molecular weight of the molecule. And you see here it's represented M plus because it's positively charged of the whole molecule. And there is a tiny peak at 86, which represents 4 molecular ion peak. The x-axis of the spectrum is represented by mass over charge, M over Z, because the charge is 1, M represents the exact molecular weight. And the most important thing is to define the molecular ion first. And in your lab reports, you have to draw the molecular structure with a positive charge on it. So the next one I want to go, when the molecule loses a fragment, and in this case, the metal group will be lost in the first place, and it will lose minus 15, which will give us 71 gram per mole for this fragment, and it's one positive charge again. So you have a tiny peak around 71. The next peak is the highest peak in the spectrum because it's the most abundant species when it reaches the detector. This is called a base peak. And the second important peak you have to identify in your mass spectrum. Again, it actually lost CH2 group, so it's minus 14, makes a mass of 57. And so on, it will lose another CH2 and another CH2, so you will see a pattern like minus 14. It will give you a 43 mass, which is represented here, and an ethyl group around 29. So above all of these, around all of these peaks, I only identified 1, 2, 3, 4 peaks, which is really useful and enough to analyze your structure. Again, this is a trial and error. You just try what can be the loss from the molecule and what the resulting fragment can be. It's a process of trial and error. I have a couple of helpful hints. They're not strict rules to follow, but they're going to be helpful when you analyze. If you see a molecule with odd number of molecular weight, and you know it has a nitrogen atom, so there could be an odd number of nitrogen atoms in that molecule. The second advice I can give you, if you see a mass of 43, it can be propyl group or acetyl group. If you know molecule doesn't have any oxygen, you can't claim that the acetyl group in the presence, right? So the phenyl group is around 77. Again, this is aromatic ring, lost one hydrogen. So it's 6 carbon with 5 hydrogens, gives mass of 77. So 91 is the benzyl group with the CH2 group attached to the phenyl ring. Again, you will not be able to identify all the peaks in your mass spectrum, like I said in the IR, so you have to look for the main fragments. The other kind of helpful hint, the common loss fragments, 15 can be a methyl group. Again, these are like helpful fragments or hints I can give you. Ethyl group is 29, 28 can be carbonyl, NH, just depends. The most important information I want to give right now, the halogens. So you see two numbers here. So chlorine can have 35 or 37. Due to the isotopes, different isotopes, halogens can have different effect on mass spectrum. This is called halogen isotope effect. Let's see the common isotopic compositions of some elements. When you check the chlorine and bromine, chlorine has 35 and 37 mass of atoms, and their abundance like 75 to 25%. When you check the bromine, the bromine with the 79 mass is 50% almost, and the bromine with 81 mass is almost 50%. So how it affects the mass spectrum? The highest mass on the mass spectrum gives the molecular ion peak, and it consists of two peaks with the 2 units apart, M and M plus 2, and their ratio is going to be 3 to 1%, 1 actually, because the percentage ratio is 75 to 25% for the chlorine. And when you look at the bromine, it has 1-to-1 ratio, and the molecular ion peak has 2 mass units apart in between. So that's a good identification of maybe if you're given an unknown, you can easily predict if it has a halogen or not. So first example I want to give it, including this propyl bromide. It has molecular ion peak, which is the highest peak in the spectrum, and they have 2 peaks apart with the 2 mass unit difference. So you can conclude it may have a bromine. Let's see if it has a loss of 79 or 81. So here is the differences between this peak to 43 is 79. So you can claim it's definitely bromine. And the other thing you can tell, because it's 1-to-1 ratio, it's again bromine. So the resulting 43 represents the propyl group mass. So even just 2 peaks identified, this is enough. Also, this is the base peak. So that's enough to analyze a spectrum. The second example is the benzyl alcohol. Benzyl alcohol has the OH group. Molecular ion peak is 108. When it lost 1 hydrogen, you can predict this 107 is this fragment. When it loses 16 from here to here, or from here to here 17, you end up with the benzyl group, which is 91. Then when it lost 14, you can go to 77. In this case, the base peak is 79 and it cannot be determined. That's fine. We identified 1, 2, 3, 4 peaks again without the base peak. That's sufficient to analyze our this benzyl alcohol structure from the mass spectrometry. I'd like to give example of one of the problems in our exercise sheet from this lab. This molecule is ethyl acetate. It consists of an ethyl group, an ester, and a methyl group here. So if you calculate the molecular ion peak, the carbon is 12 and there are 4 carbons in the molecule, 1, 2, 3, 4. There are 2 oxygens and 8 hydrogens. That makes 88. So in the mass spectrum, we see a peak at 88, so that's a good sign. So the first peak is the molecular ion peak, the whole molecule with a positive charge, because it lost an electron without losing its mass. So it's also important because all the fragments are detected should be charged, positively charged. So draw a positive charge all the time, please. And the second thing I look for is the 15 here. From the list, you can assume that it may be a metal group because the molecule has the metals and it can lose the metal groups first, definitely. It can lose it from here or here. So when you subtract 15 from 88, it will give the mass of 73. So I know the molecule lost 1 metal group. And as I said, there are 2 possible loss points. So 2 fragments are possible for this mass. One is lost this metal group, and the second fragment can lost the metal group from the carbonyl end. So if you draw both of them, it will be helpful to identify the other fragments. Then I look for the difference between 73 and 45. So the 45, actually, the difference between here to here is 28. That can be a carbonyl group loss. So this bond here is broken and left with ethyl group and oxygen. And from here to here, the loss is 30, I think. Yes, 30. And what happened is this group kind of lost in this fragment and left with acetyl group with the 43 mass. This is how you start your exercises. So we'll do these problems in the class today. So we will work on the problem sets. I want to check your answers before you leave to make sure you understand the concepts. Then we're going to run IR and mass spec of a mystery herb and spice samples. You're going to prepare diluted samples for GC and run the IR as well. Then we're going to start assigning your IR and mass spec and find out what your mystery herb and spices can be.